Let's talk about organic chemistry. Now, I know that phrase can sound a little intimidating, but what if we thought about it differently? Instead of a scary science, think of it as a language with its own rules, its own grammar, and once you get the hang of it, you can understand the incredible stories that molecules are telling all around us. So let's dive in.
I mean, you open a textbook and you see all these diagrams, letters, lines, arrows pointing everywhere. It's so easy to feel like you're missing something, right? Like there's some secret key that everyone else has to figure out what's actually going on. Well, today, that's exactly what we're doing. We're handing you the decoder ring. We're going to start with the basic rules of the game. Then we'll meet the main characters that really drive the action. And finally, we'll put it all together to read a chemical reaction from start to finish. Okay, so first things first. Before we can play, we have to understand the playing field. What are the basic principles that organize how all these molecules actually behave? The first rule is all about organization. Chemists like to group compounds into something called a homologous series. The easiest way to think about this is like genres in a library. You've got your alkanes in one section, your alcohols in another, and because they all share similar features, they behave in predictable ways, which makes studying them so much easier. Now, within these groups, you find this really key distinction. Is a compound saturated or unsaturated? Saturated compounds are, well, full. They've got the maximum number of hydrogen atoms possible, all connected by single bonds. But unsaturated compounds, they have double or even triple bonds, which means they aren't totally full of hydrogen. And those extra bonds, that's where the action happens. They're often the starting point for a chemical reaction. So how does a reaction actually kick off? You know, every story has an inciting incident, that one event that gets the whole plot moving. And in chemistry, it's almost always the same thing. A chemical bond has to break. And it turns out a bond can split in two main ways. The first is called homolytic fission. Think of this as a fair, even split. Each atom walks away with one electron from the bond. This creates two really reactive things called radicals. Then there's heterolytic fission. This is an uneven split. One atom is greedy and takes both electrons, creating a pair of charged ions. And this is a huge deal. I can't overstate this. That one simple choice right at the beginning, an even split or an uneven one, it literally sets the stage for everything that comes next. It decides what kind of reactive species are created and what kind of story is about to unfold. So once that bond has split, our main characters finally enter the scene. And these are the reactive species, the personalities, if you will, that are going to drive our chemical story forward. From that even homolytic split, we get our first player, the free radical. See that single unpaired electron? That little dot makes it incredibly unstable. It is desperate to react with just about anything to find a partner for its lonely electron. They're the wild cards of chemistry. And from the uneven split, we get our next character, the nucleophile. The name literally means nucleus-loving, which is a great clue. It's rich with electrons, and it's looking to donate a pair. So you can think of the nucleophile as the giver in a reaction. It's always seeking out a positive charge to share its electrons with. And of course, for every giver, there's a taker. The counterpart to the nucleophile is the electrophile, or electron-loving. This species is electron-poor. It's actively looking for a pair of electrons to accept. It's drawn to anything with a negative charge.
Okay, so we've got our rules and we've met our players. Now let's look at the common plots they tend to follow. You'll find that most organic reactions fall into just a few main categories, a few classic stories.
And here is the core playbook. First, you've got addition reactions, where two molecules basically just combine to form one bigger one. Simple enough. Then there's substitution, where one atom or group gets swapped out for another, like a trade. And finally, elimination, where a small molecule is kicked out from a larger one, which usually creates a new double bond.
All right, it's time. We have the rules, we have the players, we have the basic plot types. Let's put this all together and actually decode a complete reaction from the very beginning to the very end.
But wait, first we need to know how to follow the action on the page. And that's where the curly arrow comes in. This little symbol is probably the single most important piece of notation in all of organic chemistry. It always shows the movement of a pair of electrons. It starts where the electrons are, and it points to where they're going. It's basically the director's cue in our chemical play, showing us exactly what's moving and where.
The story we're going to read today is an absolute classic, the free radical substitution of methane with chlorine, and it's all kicked off by a little bit of UV light. This is a perfect example because it uses all the concepts we've just talked about.
Now, this reaction has a classic three-act structure. First, you have initiation, which gets the whole thing started. Then you have propagation. That's the main action, where the cycle just keeps repeating itself. And finally, termination, the grand finale where it all comes to a stop.
So, Act 1, initiation. A little blast of UV light provides the energy needed for that homolytic fission we mentioned, that nice even split. A stable chlorine molecule breaks apart into two super-reactive chlorine-free radicals. And just like that, our first key players are on the stage. Now for Act 2, propagation. This is the heart of it, the self-sustaining chain reaction. So first, a chlorine radical comes along and attacks a methane molecule. It steals a hydrogen atom, and that creates a brand new methyl radical. This new radical is also unstable, so it immediately attacks another stable chlorine molecule. And look what happens. It creates our final product, chloromethane, but, and this is the crucial part, it also creates another chlorine radical, which can now go back and start the whole cycle all over again.
And finally, Act 3, termination. How does the story end? Well, it stops when any two free radicals happen to bump into each other and combine. For example, a methyl radical might meet a chlorine radical, and boom, they form a stable molecule. Once these super-reactive radicals are paired up and taken out of the equation, the chain reaction just fizzles out.
And there we have it. We just did it. By understanding how bonds break, who the key players are, and this three-act structure, we didn't just stare at a bunch of random symbols. We read a coherent story. We followed the plot of how molecules interact. We've actually learned to read the language of chemistry. So let's just quickly recap what's in your new toolkit. You can now spot how bonds break, whether it's an even split or an uneven one. You know the main characters, the radicals, the nucleophiles, the electrophiles, and what motivates them. You recognize the basic plot types, and you can follow the full story using curly arrows to see a step-by-step mechanism.
You officially have the decoder ring. The language of organic chemistry isn't a secret code anymore. So the only real question left is, what other amazing molecular stories are out there, just waiting for you to read them?